Hi everybody, welcome back. In the last few videos we have gotten more into using the concept of momentum and its conservation to calculate what should be the effects of objects when they collide with each other. And then we got into this idea of impulse as a change in momentum. And this was a concept that we first introduced as impulse equals force times time, and then realized that, hey, this impulse is actually change in momentum according to Newton's second law. Now we will look at situations where the force on an object is not constant during an interaction. So we can see a situation involving this right here in this graph. In this graph we have two different collisions that both involve the same change in momentum. Using arbitrary units, this could model, say, the typical physics teacher jumping off of a chair experiment. In the first case with the nice high graph, this would be where the teacher locks the knees, and in the second case, this would be where the teacher intentionally bends the knees. In either case, the change in momentum is the same because in either case, the teacher is hitting the ground with the same speed, assuming they jump from the same height. But the time over which the teacher goes from hitting the ground to, at some speed, to rest is different depending on whether the teacher bends the knees or locks the knees. As you can see, locking the knees results in a noticeably larger force, which of course can do noticeably more damage. So just as we had work being the area under a force versus position graph, if force was constant, we had work equals force times distance. Well, if impulse is constant, if force is constant, impulse is force times time. But if the force is not constant, well, same idea. You can take the area under the force versus time graph. In fact, in general, in any situation where you have two variables being directly linearly related, if you have variable A equals variable C times variable B, then if variable C is something that fluctuates, then you can make a C versus B graph, and the area under that will be the change in variable A. So let's see how that works. Consider a problem where you have Calvin and Hobbes on a sled, and let's say the sled is initially going toward the right at 11 meters per second. And by initially, I mean actually at the time 30 seconds later when we actually start plotting the force acting on the sled versus time, such as in this graph. This is the graph that will be used to model this motion of Calvin and Hobbes. So what we can see is that the force starts off being constant, but then the force actually does change. But we can figure out an impulse between any two time intervals by taking the area between the function and the time axis, which is kind of in the middle of the graph. That is the f equals 0 axis. So this problem actually comes off of a worksheet that I usually give my students, and we're mainly going to look at first figuring out how the impulse relates to the graph, and then how this impulse that we get from the graph relates to the velocity of Calvin and Hobbes after certain times. So keeping in mind this graph, well, let's consider part A. How do you find the impulse from 30 to 60 seconds? Well, we just said that. Impulse is the area of a force versus time graph. So you take the area between the graph and the axis of zero force, that is the time axis, over the interval from 30 to 60 seconds. That is actually just this rectangle. And then B, which 30-second time interval or intervals contains a net negative impulse. Well, those will be situations where the overall area under the graph during that 30-second interval is negative. Well, it's negative if you have more below the time axis than above. Well, clearly that's the case from 90 to 120 seconds, and also from 120 to 150 seconds. Now, between 150 and 180, it starts as negative and it ends as positive. And you see this is a straight line that crosses the time axis exactly halfway between 150 and 180. So overall, the negative that you get from 150 to 165 will be canceled by the positive that you get from 165 to 180. So it's only from 90 to 120 seconds and 120 to 150 seconds. Now, part C, calculate the impulse from 30 seconds to 60 seconds. Now, even if you knew nothing about impulse being area under force versus time graph, you could realize, hey, from 30 to 60 seconds, the force is a constant 12 newtons, so I'll just multiply the force by the time. So you'd have 12 newtons times 30 seconds, and you get 360 newton seconds, or 360 kilogram meters per second. But here, it's the area of a rectangle. Well, that's base times height. The base is 30 seconds, and the height is 12 newtons, so it works out. But the point is, it would have worked out even if the force wasn't constant. It's always the area, because any one of these areas can be broken down into a whole bunch of little rectangles, where you imagine the force being approximately constant over a very thin rectangle. How about the impulse from 90 to 120 seconds? Well, that's the area of this triangle. What's the area of a triangle? It's 1/2 base times height. But in this case, the height is negative. The height is negative 20 newtons. In other words, you're going from, basically you could think of it as final minus initial, so negative 20 minus 0. So your height is negative 20 newtons, the base is still 30 seconds, so you get an impulse of 30 times 10, because half of 20 is 10, and there's a negative there, so negative 300 newton seconds. Hopefully this makes sense, because this is a negative force. A negative force means that it's acting to the left. Well, if the object is moving to the right, a negative force is going to decrease its momentum, or make it increase in the negative direction. So the negative sign on this should make conceptual sense as well. How about the impulse from 150 to 180 seconds? Well, again, we mentioned this before, the negative red area is canceled by the positive green area. So the impulse during that time interval is 0. So therefore, the change in momentum from 150 to 180 seconds is 0. It started off negative, and then you had positive. Overall, it cancels out to give 0 impulse, that is 0 change in momentum. How about this next one? Calculate the sled's velocity at the 60-second mark. So remember, in this case, we're going to use the fact that the change in momentum is equal to the impulse. Now, we have a couple of little parts like this, so I'm going to do them in 2 different ways just to show you that they can be thought of in 2 different ways. I'm going to say, okay, well, the final velocity, that is the velocity at 60 seconds, is equal to the initial velocity, that is the velocity at 30 seconds, plus the change in velocity from 30 to 60 seconds. Well, what is change in velocity? We know that momentum is mass times velocity, so change in momentum is mass times change in velocity. In other words, change in velocity is change in momentum divided by mass. Now, if you're used to thinking of it the other way, in other words, pi plus j equals pf, that's fine. We're actually going to do it that way in the next part. But I did want to show you this, which for simple sets of numbers can prove to be a little bit of a shortcut. So we already know the change in momentum is 360 kilogram meters per second. Again, impulse is not momentum. It's the change in momentum that occurred from one time to another time. The change in momentum that occurred during an interaction or a collision. So that change in momentum is 360 kilogram meters per second. Well, since momentum is mass times velocity, so change in momentum, that is P final minus P initial, is equal to mv final minus mv initial. You can imagine factoring out that m, so you'd have m times quantity v final minus v initial. Well, v final minus v initial is just delta v. So that's why delta p equals m delta v, as long as the mass doesn't change. So the mass, therefore, that's 45 kilograms. And, well, let's see now. I think we can do this in our head. I know that 45 times 2 is 90, okay? And I also know that 36 divided by 9 is 4. So 360 divided by 90 is also 4. But we had to multiply by 2 to get there in the first place, so we actually have 360 divided by 45 is 8. So our delta V is 8 meters per second. So since we know what delta V is, the change, we know what we started with, now we know what we end with. What we end with is what we started with plus the change. So there we go. V final is V initial plus delta V, and that gives us 19 meters per second. And that's a pretty fast sled. This thing is going over 40 miles per hour. Okay, next part, calculate the velocity at the 120-second mark. So in this case, well, we need to add up 3 different areas, or 2 different areas. If you want to call the green part a trapezoid, that's fine. Then we just have two different areas. Here, we're going to break the trapezoid down into a rectangle plus a triangle. So we'll call it three different areas. So first, we're going to find the impulse from 30 to 120 seconds, and then use our initial velocity at 30 seconds and add the change in velocity, which actually we're going to do it straight from impulse being change in momentum, and end up getting our final velocity. Now, another way of doing it would just be to calculate the two areas, the area from 60 to 90 seconds, the area from 90 to 120 seconds, and add those up and get our net impulse from 60 to 120, and then use the fact that the final velocity, that is now the initial velocity at 60 seconds, was 19 meters per second. But in any case, we're actually just going to go back to 30 seconds. Now note that we've already calculated two of these impulses. We calculated the impulse from 30 to 60 seconds, and we calculated it from 90 to 120 seconds. So you really don't even need to show this work right here on the first calculation and the third calculation, because those are calculations we've already done in earlier parts. But we do need to show the part from 60 to 90 seconds. That is this 1/2 base times height. This green triangle, so to speak, right here with a base of 30 seconds and a height of 12 newtons. In any case, once we work all of these out, we get the 360 that we had before minus the 300 that we had before. That is actually plus the negative 300 that we had before. So that gives us 60 plus 180 gives us 240 newton seconds. That is 240 kilogram meters per second for our impulse. That is our change in momentum. Well, okay. P initial plus J equals P final. Remember, that's the definition, well, not really the definition, but that's the result of the impulse momentum theorem. So kind of just thinking back to the previous unit, well, initial energy plus work equals final energy. Well, initial momentum plus impulse equals final momentum. Well, what's a momentum? It's a mass times velocity. So everywhere I see a P, I'm going to plug in an mv. And I'm solving for my final velocity, so I'm going to divide both sides by m. That gets rid of it on the v initial part, but then we have a j over m. Now we can plug in our numbers. We just calculated j, that's the 240 newton seconds, that is 240 kilogram meters per second. And when you work out that calculation, you get a final velocity of 16.3 meters per second after 120 seconds. And again, that is a pretty fast velocity. I mean, this is about 35 miles an hour, so pretty fast sled. But Calvin and Hobbes were always pretty wild on their sleds. Okay, how about calculate the final velocity at the end of the ride, given the whole graph, that is at 180 seconds, starting at 30 seconds. Well, same idea. The impulse is equal to the total sum of the areas under the force versus time graph. Well, we already got it from 30 to 120 seconds. I'm not going to bother recalculating that. But we still need to calculate from 120 to 150, and we actually already calculated from 150 to 180. We know that that part's 0. So the only new calculation we need to do is from 120 seconds to 150 seconds, and that's an easy rectangle. Yeah, I know it looks like a square, but these are different axes, so you can't really call it a square. It's a rectangle. So you have 240 newton seconds, which we already calculated in part G. You have 0 newton seconds from 150 to 180, which we had calculated, I think, like in part C or D. And then the new calculation is the base times height. I probably should have added in another step saying, it's like, okay, J 30 to 120 plus base times height plus J 150 to 180, and then plugged in the numbers. But in any case, our base is 30 seconds, and our height is negative 20 newtons. You plug those in, and you get negative 360 newton seconds. So the overall impulse that Calvin and Hobbes received was negative, so they're going to slow down. Let's see how that works out. P initial plus J equals P final. Everywhere I have a P, that's an mv. I divide both sides by mass to get my V final by itself. So V final is V initial plus J over M. No, you definitely cannot start from this equation. You have to start from the definition stuff. That is the basic equation. And then you plug in your numbers. We already know that 360 divided by 45 is 8, but this time there's a negative sign tacked on. So V final is 11 meters per second minus 8 meters per second. That is 3 meters per second. So at the end of the ride, they're still going 3 meters per second, which is like 7 miles an hour. Okay, now, what would the sled's initial speed have had to be if we wanted them to come to a rest at the end of the ride? Now, you could do a shift in reference frames here and say, hey, I want to work in a reference frame in which I'm going 3 meters per second toward the right, because I know that's what their final velocity is. Well, in other words, if I'm going at 3 meters per second toward the right, I'm going to observe them ending at rest. Well, if I'm going 3 meters per second toward the right, then that initial velocity of 11 meters per second looks like 8 meters per second to me. That's actually a perfectly valid way of doing a problem like this. In other words, thinking about it in terms of a relative velocity. But you would have to explain that in enough detail to convince the grader that you know what you're doing. Let's look at it from an impulse momentum standpoint. We know that the impulse for the entire ride is negative 360 kilogram meters per second. Well, that's the change in momentum. So if we want the riders to come to rest at the end, that means their initial momentum must have been 360 kilogram meters per second. Because obviously their final momentum is 0. PF equals 0. I forgot to write that down. PF equals 0. So if PF equals 0, and delta P is negative 360 kilogram meters per second, because that's the area under the whole graph, we calculated that in part H. So that means P initial is 360 kilogram meters per second. That is 360 Newton seconds. Well, P equals mv, so V equals P over m, so V initial equals P initial over m, where m is mass. So you just divide by mass, and you get, just like we expected, 8 meters per second. So that is how you can use the area under a graph not only to calculate an impulse, which is something that's a little bit more abstract than what we're used to, but using that impulse to figure out either an initial velocity or a final velocity given certain types of situations. So with that in mind, we're now at the end of our discussion about impulse and momentum. So consider these questions. Maybe think about them with a buddy. So first, can a fan cart drive itself by using a sail? And if so, how would you do it? Second, as an object drops, its momentum increases. So if dropping increases an object's momentum, how can you reconcile this with the conservation of momentum? I mean, conservation of momentum is a law. You can't get around it. So what's going on? And finally, from a passenger safety viewpoint, should a car be built for inelastic collisions, or should it be built for elastic collisions? So think about that. And I'll leave you with these 3 items to think about. Feel free to discuss your answers in the comment section. And otherwise, thank you for watching.